Okay, I have on the board a problem that could, but we'll see what we have here. Has to do with the central limit theorem. Let's start with this. Example 1. Teacher salaries in Tennessee. Suppose the average teacher's salary in Tennessee is $37,764. Assume a normal distribution with the standard deviation of the population sigma equal to $5,100. What is the probability that a randomly selected teacher's salary is greater than $40,000? Again, when I was working with the normal distribution problems, I would always draw a picture. So there's my normal distribution. It says it's normal. And our mean was this, 37 whatever. We want to know what's the probability of something being greater than 40,000. So that's to the right of 37,764. So we want to know what the likelihood of that happening is. That's what we want to know. So first thing, what equation should we use here? Well, we could, if you wanted to, use the following. You could use this equation here because if you look at this, what's the probability? As I mentioned earlier, this is a randomly selected teacher, one teacher. That equation was used when we chose an individual out of the population. But now that you know the central limit theorem, you know that this equation will always work. Why don't we use this equation? Let's use this equation. Okay. So we're going to get 40,000. Whoops, I'm running out of room. I am going to put it over here. 40,000 minus 37,764 over 5,100 divided by the square root of 1. Square root of 1 is 1. 5,100 divided by 1 is 5,100. It reverts to this equation here. This becomes this equation. Now, if we type that in, let's do this right quickly. 40,000 minus 37,764 divided by 5,100 equals 438. So this gives us a z value. So this is actually approximately 0.44. This is what we're going to look up on our z table. So if we look up 0.4, we look up 0.44, we get 0.6700. Something's not right. Okay, my answer's wrong. Who knows why my answer is wrong? I noticed it because that's 0.67. That's greater than a half. What does the table give us? I've said this many times, and here I violated. It gives us the area in the red. I want the area in the black. So I take 1 minus this number, and we get 0.33. So 33% of the time, we will find a teacher who makes more than $40,000. Now let's look what happens here. Suppose we have a sample of 25 teachers. Everything else is the same. Let's set this up. Normally I would draw this again, but everything's identical other than n. N is now different. So we have z equals 40, 1, 2, 3 minus 37,764 over 5,100 divided by square root of 25. Let me just make sure I got all the numbers in right. 40,000, 37,764, 5,100, and 25. So if we type this in, uh, 40123 minus 37,764 divided by we get 2.192, so this is approximately 2.19. So if we look this up, 2.19, we get 0.9857. 1.1234 minus that. 1 minus 0.98. 0.143. Okay, so that's how you do that. Now, one thing I want to point out is notice that this was very common, 33%. That's 1/3, approximately 1/3. 1/3 of the time, an individual may have over 40,000. But to get a group whose average, a group of size 25, whose average is over 40,000, is less than 2%. Very, very difficult. Think about this. In a classroom, I can pick any individual. What's my chance of getting a high GPA? That's pretty good. But to get a group of 5 people that all have a very high GPA is hard because, you know, you're going to get a high GPA. Let's suppose you get the top 2 high GPAs, but then you get 2 low ones. Right there, it brings you toward the center, hence the central limit there. Whenever you're getting a group, you're going to get some highs, some lows, and some in-betweens. There's a tendency for the sample size to be near the middle. It's hard to be an extreme up or extreme down, as is shown here. Getting a sample, the chance of being far away from that mean is very rare, whereas if you're pulling an individual out, you could get the largest value, you could get the smallest value. But that's what's called the central limit theorem. Notice what happens also. Well, I just explained it. Right here, we have this going on, but when you have this square root of 25, what's happening to this graph, which I did not draw, is this doing this type of thing like I said. Here, let's suppose the highest salary is 50,000. Is there any way to get an average down here at 50,000? No, because even if you chose the person making 50,000, as soon as you choose somebody else, that number has to be lower, and that will lower the average. So all I'm pointing out is when you do the central limit theorem, standard deviation is very narrow, and it starts pinpointing on what the actual mean is. That's one thing that's going on. I hope this was helpful. I will pause and give us another problem. Actually, I'm going to stop recording